Hi, Dr. Robin here. Today we're going to be talking about calorimetry, the study of heat. In this video, we're going to talk about two ways that we can determine how much heat will be required to change temperature a given amount: heat capacity and specific heat. Let's start with heat capacity. This is defined as the amount of energy needed to heat an object by 1 degree Celsius. The heat capacity of a particular object has to be determined experimentally. This formula helps us use heat capacity to determine a temperature change. Q equals C delta T. What do those variables mean? Well, Q is the amount of heat energy that is put into the object, C is the heat capacity of the object, and delta T is the change in temperature that occurs. Scientists use the symbol that you see here, delta, to represent the change in a quantity. The change in anything is calculated by subtracting the initial or starting value from the final or ending value. So in this case, for a change in temperature, delta T, that would be the final temperature minus the initial temperature. So let's try a problem to see how this formula can be used. Let's say that we've experimentally determined the heat capacity of a pot in the past, and we've found that its heat capacity is 1,278 joules per degree Celsius. As the pot was sitting on the stove, someone accidentally bumped the burner and turned it on. By the time they shut off the stove a little bit later, the pot had absorbed 25.7 kilojoules of energy. So how much did the pot heat up while the burner was on? Let's look at our formula again. Q equals C delta T. The problem asks, how much did the pot heat up? And so your first impulse may be to find Q. I mean, that's heat, right? But in fact, what we want to know is how much hotter the pot got. In other words, how much the temperature changed. So what is Q then? It's heat energy. Do we see anything in the problem that might represent that? Sure. 25.7 kilojoules of energy. To solve for delta T, we also need to know the heat capacity, C, which is given right here. Let's plug those numbers into the equation. Can we now solve for delta T? Not really, because our energy units on the left side are in kilojoules, while those on the right side are in joules. Here's our conversion factor, which tells us that 25.7 kilojoules equals 25,700 joules. And now we solve for delta T by dividing through by 1,278 joules per degree Celsius. So our value for delta T is 20.1 degrees Celsius. As a reminder, this does not mean that our final temperature is 20.1 degrees Celsius. It means that the pot is 20.1 degrees Celsius hotter than it was before the burner was pumped on. Next up, we're going to talk about specific heat, which is defined as the amount of energy needed to heat 1 gram of a substance 1 degree Celsius. I know that sounds a lot like the definition of heat capacity, so let me call out the difference here. Heat capacity talks about how much energy you need to heat an entire object, while specific heat is based on the amount of mass that's available. In other words, specific heat is an intensive property. You can use it just as easily with 5 grams of water as you can with 5 metric tons of water. This is the equation that helps us use specific heat. Some part of it may look familiar. Once again, Q is heat energy, delta T is the change in temperature, S is the specific heat, and M is the mass of the substance. You can see what's changed between this and the previous equation is that we have mass and specific heat where we had heat capacity before. Let's try using this in a problem. This question wants to know how much energy would be required to heat 1,000 grams of water from 25 to 100 Celsius, which is essentially what you do when you make pasta. So let's start out by using our equation. The problem is asking how much energy, which tells us that we are solving for Q. We need to find values for the other 3 variables in the equation. Do we have mass? Yes, it's 1,000 grams. Do we have the specific heat? Yes, it's given to us here. And do we have the change in temperature? Not exactly, but we can use the definition of delta T to calculate it. We have starting and ending temperatures. Sometimes people have a bit of trouble figuring out which is the starting temperature. In this case, our keywords are from and to. 25 Celsius must be our initial or starting temperature, while 100 must be our final temperature. Let's now plug our numbers into the equation. Our delta T works out to be 75 degrees Celsius. If you double check the units, you can see that our grams cancel, our degrees Celsius cancel, and we're left with the units of joules. When we do the multiplication, we see that we end up with an answer of 313,800 joules, or 313.8 kilojoules. This problem shows a slightly different approach to using the same equation. What is the specific heat of silicon if it takes 192 joules to raise the temperature of 45 grams of silicon by 6 degrees Celsius? Here we are asked to find the specific heat rather than the energy. In fact, this is how people come up with the values for specific heat that you find in tables, by measuring the temperature change for a given energy input. So we're trying to solve for S here. Let's isolate S on one side of the equation, first by dividing both sides by delta T, then dividing both sides by M. This tells us that S equals Q divided by M delta T. Now let's find the values we need to plug into the equation. Q is heat energy. Although there's nothing in the problem that actually says the word energy, there's this bit here that has the unit of joules that tells us it is an energy measurement. Our mass is 45 grams and our change in temperature is 6 degrees. Let's plug those numbers into the equation. Running them through the calculator, we get a specific heat value for silicon that is 0.71 joules per gram degree Celsius. Our last problem here is probably the most complex. What it describes is a piece of iron at a temperature of 500 Kelvin, which is pretty hot, coming in contact with a piece of copper at 295 Kelvin, which is basically room temperature. The problem says they are left to reach thermal equilibrium. What is thermal equilibrium? Well, think about what happens anytime you get something really hot resting against something cooler, like if you put a mug of tea down on the table. Over time, the table, at least the part where the mug was, warms up a bit and the mug of tea cools down. And if you leave them there long enough, they end up at the same temperature. That's thermal equilibrium. So in this case, we have our hot iron. I've outlined it here in red to remind you that it's hot. And our copper, which is outlined in blue to remind you that it starts out cool. What's going to happen? The copper is next to something that's hot, so it will heat up. The iron is next to something cooler, so it will cool down. And as with our mug and table, they'll end up at the same final temperature. In order to understand how to do this problem, you need to understand that there are two things happening here. First of all, the copper is gaining heat energy. How much heat energy is it gaining? We use the specific heat equation to tell us. Now notice that this is slightly different than what I wrote before. I've put a subscript of Cu to tell us that this is what pertains to copper. The mass of copper, the specific heat of copper, the amount the temperature of copper changes. The second thing that's happening is that the iron is cooling down. What that means in thermal terms is that it's losing heat energy. How much energy is it losing? Well, that is also determined by the specific heat equation. This time I've used a subscript of Fe to indicate that this is the mass of iron, etc. Now, the important thing you have to realize is that these two energies are related. The reason is that the energy that is used to heat the copper is coming from the iron. How much energy is used to heat the copper? The exact same amount of energy that is coming out of the iron as it cools. And so I've written it here. The heat energy of copper will be the opposite of the heat energy we calculate for iron. Let's now take these two expressions and plug them into this formula and see what we can do with them. So here we have those same two expressions plugged into the formula. That's a lot of variables. Let's see what we can do to simplify this. First, we have the mass of iron. The problem tells us that's 85 grams. Next, we have the specific heat of iron, which is 0.461 joules per gram Kelvin. We have the mass of copper, which we see from the problem is 24.5 grams, and the specific heat of copper, which is 0.377 joules per gram Kelvin. Let's plug those numbers into our equation. At first, it honestly doesn't look a lot better, but what we can do is multiply those constants together to get this expression here. The unknowns we have left are the delta T for iron, which is the starting temperature of the iron minus the final temperature, and the delta T for copper, which is the starting temperature of copper minus the final temperature. I'm going to rewrite our delta T's to take that into account. Remember that our final temperature for the iron and the copper will be the same temperature. So I've represented both here with T sub F. That's what we're trying to find. So let's look for values for the other temperatures. The starting temperature of iron is 500 Kelvin, and the starting temperature of copper is 295 Kelvin. So let's plug those numbers in. Now I'm going to simplify this by distributing the coefficients, 39.5 from the iron side and 9.2365 for the copper side, across what's in the parentheses. That gives us these numbers. Let's put every factor containing T sub F on one side and everything that's a constant on the other side, and that gives us this expression here. Then we can divide both sides by minus 48.7365 to get our final temperature of 461 Kelvin. Does our answer make sense? Well, it's between the original iron temperature of 500 and the starting copper temperature of 295, and it's closer to the original iron temperature, which makes sense because there's more iron than copper. In closing, I want to say a couple of things. First of all, when you look at specific heat values, you'll see a couple of units, either joules per gram degrees Celsius or joules per gram Kelvin. Both of these mean the same thing. A change of 20 degrees Celsius is the exact same as a change of 20 Kelvin. No matter what your energy change, it will be the exact same magnitude in degrees Celsius or Kelvin. Finally, both specific heat and heat capacity are tools we use to figure out how much energy we need to add to a system to change the temperature of the system. So how do you know which to use? Well, it really depends what your system looks like. Is it made up of one substance, like iron? Great, you use specific heat. But if it's made up of a mix of substances, like the iron and wood in this hammer, you'll have to use heat capacity. I hope this was helpful, and I look forward to seeing you again soon.